All right, so I'm going to be talking a little bit about what chemical engineering as it is aligned with optoelectronic materials and processes. And there are a number of us in Chemie at Georgia Tech who are part of the COPE Center, and I'll be bringing in some vignettes about where they have an interest. It relates to a lot on polymer and organic materials, and also some related to inorganic materials. But all of it is largely focused towards semiconducting materials and processes, or conducting materials, effectively in the broad class of optoelectronics. All right. Using the laser pointer isn't going to work to change slides. All right, so talking about polymers first. Really, if we're looking at hybrid materials and processes for optoelectronics, we're interested in aspects of sort of design and development of new materials chemistry. So there are certainly aspects where some of what we do is very aligned with and very interactive with chemistry, also with material science. We're interested in developing sort of structure-process-property relationships, not just the structure of the material and how that may relate to the material's properties in a device architecture, but we're finding increasingly that the actual process that's used for fabricating the device plays a very critical role in materials performance in a given structure. So how are these factors related to each other, and what is going to be more significant, and how do they interrelate? And then understand more on a fundamental level the mechanisms associated with thin film formation. All right, so basically, this is an example of an AFM image of poly-3-hexylthiophene, and you can see that there's an organized nanofiber structure in that film. Depending on how you process it, you can get something that looks like this or something that looks very different. And those materials behave differently. So this cartoon of looking at the structure and the properties and the processing and how they all interplay with each other ends up being quite important. And I think a lot of what we do in chemical engineering is in this space. All right, so if we look at sort of order and disorder in polymer systems, and you've seen this earlier this morning, certainly the semiconductor polymer properties are going to be very dependent on the morphology of the final thin film. That is dependent on the process that's used, and the development of the microstructure, basically nanostructure all the way through to macrostructure in the thin film, really is not well understood. All right, and if you look at the AFM images up here, these are all thin films of the same sample of poly-3-hexylthiophene that have been processed differently. And each one of those has different characteristics when used in a device. That didn't work. Okay, here we go. All right, so if we look at the role of microstructure, that's certainly been explored over the course of a number of years, where there have been discussions of the radioirregularity-dependent texture of P3HT, the effect of polymer molecular weight, and certainly the semiconductor dielectric interface is also very important in how the polymer chains align on the substrate. And then more recently, we've been looking at understanding the evolution of that thin film structure during solvent evaporation. And we've seen that the films in a device architecture undergo changes in alignment between polymer chains, and we've also looked at those mechanisms spectroscopically to try to understand what's going on and relate that more broadly to pi-conjugated materials. All right, and then we did some work on processing and also the impact of radioregularity and how important it is to get very tight control of the materials properties in order to get control of device properties. All right, so first looking at processing, what can you do? What are some of the changes that you see? Well, this is an example of what can happen if you do ultrasonic irradiation of a solution of P3HT in chloroform prior to depositing the material on the device. All right, so first, if you look at the solution state, you get a, if you look at the blue curve, you start to see bands that are in a longer wavelength region that appear to and are reminiscent of the solid state absorption bands of P3HT. And also in a solid film, you start seeing vibronic structure in that solid film. So it appears that the material itself is somewhat more ordered. If we look at the crystallinity of those films, looking at the AFM images, as we increase the sonication time, we start to see large crystallite formation, and that increases with the time the solution has been sonicated. If we look at the X-ray patterns of those same films, at least it appears that the films are becoming more crystalline as we are sonicating the solutions for a longer period of time. If we look at the charge transport characteristics as measured by the mobility in a device architecture, we see that the mobility starts to saturate after about 2 minutes or so of ultrasonication of the precursor solution. And there's also about a 2 order of magnitude increase in mobility. So just because we have increased crystallinity, that does not mean we have increased mobility. So the two are not strictly connected, though there is a connection. And what we believe is happening is that there's a percolation type charge transport mechanism where we have a multiphase morphology where we have disordered regions, quasi-ordered regions, and more ordered regions where if you look in this area of the film that is not, it comes from a solution that's not been sonicated. You see basically an amorphous structure. There are some regions that are a little bit more ordered, such as here. And then certainly here, you do see relatively large crystallites being formed. All right, so we believe that we need to have sort of a balance of all of these 3 regions in order to be able to get good connectivity between aligned regions of the polymer in order to maximize the charge transport characteristics of the films that we obtain. All right, so if we look at conducting channel formation more broadly and start to interrogate a droplet as solvent is evaporating, all right, we see that the drain current starts to fluctuate as the film is being formed. Polymer chains rearrange as a function of time, and more than likely there's percolation type effect going on. There may be bulk versus interface effects in this particular case, but we'd really like to understand what's happening during that process as the microstructure is developing. All right, so we started looking at the system with Raman spectroscopy, and what we were able to find is that there was a lyotropic liquid crystalline phase that is appearing in the film as solvent is evaporating, and it may be coincident with a very sharp increase in the current when we're seeing it. All right, so given that there may be long-range order associated with that LC phase, there may be consequences for macroscopic charge transport. So can we now, through processing, be able to control that long-range order in order to enhance transport in a device system in a way that we would like? All right, and these are just the Raman spectra that we had obtained that support the premise that we are forming a allotropic liquid crystal. All right, so if we do the same experiment, this is looking at the Raman signal over a period of time. Here's the sharp increase in drain current. If we look a little bit more closely in just this region of B to C, that is just a 2-minute increment, we see that in the region of where we would expect to see crystalline P3HT, the Raman signal is very weak, reminiscent of amorphous P3HT. And as solvent continues to evaporate, we see the appearance of bands that are essentially identical to the Raman signals that are seen from a crystalline phase of poly-3-hexylthiophene. So again, during this very short transition period, we are seeing crystalline regions of the polymer being formed. All right, and we can deconvolute the peak where we believe that we're starting to see very rapid nucleation of P3HT and organization of the polymer chains in the solidifying film. All right, so we're taking that a few steps further and now trying to explore a combination of on a fundamental level, but then also from a design and synthesis perspective, can we now use liquid crystallinity as a means of being able to have the ability to change the processing of the material during fabrication of a device, and as a result of liquid crystallinity, end up with a more ordered film, and as a result, a film that would have enhanced electrical properties. All right, so one attempt at that was looking at benzothiodiazole oligothiophene based low band gap donor acceptor copolymers, where we've used the electron deficient BT unit along with the electron rich thiophene unit. If we look at the photophysical properties, we see that from the 6-thiophene material, that there is a relatively long wavelength band. If we go to the solid state material, we see that there are 2 absorption bands, one that is reminiscent of intramolecular charge transfer between the donor and acceptor units, another one that is reminiscent of the thiophene-based pi-pi star transition. Thermal properties, the polymers themselves appear to be relatively thermally stable. Decomposition temperature around 350 to 450 degrees, depending on composition and molecular weight. The materials also have melting and recrystallization temperature. Also, there are 2 thermal transitions in the 6-thiophene analog, and there appears to be a mesophase in the range of about 70 to 150 degrees C. All right, in addition to that, a lower molecular weight analog of the 6-thiophene material is birefringent when looked at under a polarized optical microscope. So we believe that liquid crystallinity is allowing us to manipulate the structure of the thin film with a little bit more latitude. Looking at the transport characteristics of that polymer, we can see that there are hole mobilities up to about 0.75 centimeters square per volt second. That mobility is dependent on the anneal characteristics of the process, and we're exploring molecular weight and substituent effects on the polymer right now to see whether we can enhance those characteristics still further. And, you know, basically the hole mobilities correlate with the degree of molecular ordering in these systems. So, an aspect of what one can do with processing and looking at a broader engineering approach, we've also started working with Martha Grover in chemical engineering and thinking about how we might be able to use modeling to improve device performance. All right, so if we look at sort of morphology of typical semiconducting polymer films, certainly there's a process that is being used, device characteristics, and a lot of different chemistries that can be used to prepare the materials. We don't fully understand the relationships between each of those components. So by taking a modeling approach, can we now start to simplify the approach and the steps we take in defining the chemistries that we use and then being able to get reproducible and reliable measurements in a device architecture and do that through variations in the process and understanding the morphology that we get from that process. All right, so basically we can select a set of design variables. We can determine a chemical structure and vary that structure in a known way so that we would initially select a set of candidate materials as a model system, incorporate that into a model, and develop an experimental design where we could now test that model. All right, and then we could, from the results of the design, we could run the experiment, do the characterization, and then do a feedback mechanism. All right, so as an example of where Martha Grover has been able to use that kind of an approach very effectively is the copper zinc tin sulfide system, CZTS, where through doing experimental design, she's been able to explore the morphology space that one can achieve through processing and be able to control it. All right, so materials for optoelectronics. They're polymer materials that are near and dear to my heart, but they're also inorganic materials. And there are a lot of emerging applications for semiconductor nanowire structures. And I just got a few slides that will show some of the work that Mike Filler in chemical engineering has been doing more recently. All right, so most nanowires are one-dimensional, and what Mike's group is doing is designing novel precursor chemistries along with the synthesis protocols to allow development of these 1D structures in a fairly complex design in order to induce the kind of performance that they would like to achieve. Right, so This is an example of the kind of control that they've been able to achieve strictly through processing of inorganic structures. Basically, they've been looking at using vapor liquid solid synthesis as a way of developing and manipulating surface plasmons and then exploring where those structures could be implemented in a device. All right, so I'm going to close with that, but say that, effectively it's a combination of understanding molecular structure, understanding the chemistry of a system, in conjunction with the processing that allows us to really influence electronic properties and device performance. And that's going to influence the kinds of device architectures that we may be able to achieve on a large scale in a fabrication environment. All right, so I think we need to understand all aspects of material structure. We need to be able to understand and control the processes where those materials are being used as well. And I totally buy into the idea that materials can provide the basis for novel modules, and these modules can then get integrated into devices that can apply to many sectors of our economy, whether it is electronics, plastic electronics, optoelectronics, photovoltaics. There are a lot of different applications where materials for devices can play a role. But it's really important to understand all of the interrelationships. So I'll close just with a listing of the chemical engineering associated faculty involved in COPE. You can see more about the research aspects of chemical engineering at Georgia Tech if you visit the website. There are a lot of different activities surrounding not only optoelectronics, but a lot of interest in energy and sustainability, and a vast array of other areas. I would also be remiss if I didn't thank my collaborators on parts of what I talked to you about today, Mohan Srinivasaro in MSc and David Collard in chemistry. I would also have to thank funding agencies that are primarily NSF and AFOSR. Also have to thank Georgia Tech, and thank you for your attention, and I'll ask if you have any questions. Thank you. Joe.
Also, have similar approaches to what people take to build liquid crystal displays, using surface modifiers that present certain anchoring forces.
Mm-hmm.
Has that been employed? Have you guys employed those sorts of approaches in terms of trying to get some better control of order in
Not yet.
polymers?
Not yet. It's something that we're interested in doing. I think we're still at the stage of, I think a lot of conjugated polymers that have been used for devices and reported in the literature may or may not have liquid crystalline characteristics. There's certainly reports that, sort of somewhere buried in the article, this appears to be liquid crystalline. No one has talked about the possibility of liquid crystallinity in P3HT as solvent is evaporating. And that's something which we would like to pin down and understand a little bit better. in order to see whether there is, and investigate whether there's a direct correlation between having liquid crystalline characteristics in a polymer system is a benefit for the process to be able to induce better ordering. I think if that ends up being the case, then looking at exactly what you're suggesting is a next step. We're trying to look at it. There are multiple dimensions to the problem, and we want to try to understand what the relationships between the various variables are, and we want to try to avoid changing a dozen variables and deciding it's this one that is, we want to be able to, yeah, this is important or not. So, yeah.
On device and watching, I think it was whatever has it evaporate, the salt evaporate.
Yeah.
Was the device what potential was applied the whole time? Does that have an influence on ordering the electric?
That's a very good question. We don't know the answer. So we have, the Raman studies that I showed here were not done on the device. The Raman studies were done on a droplet of solution that had been dropped on a glass slide. The device studies obviously were done on a device architecture, and there is a field applied if we're going to be measuring current. We're trying to explore whether for the device there is an effect of the current or not. That experiment is not as trivial to do as one might think. So we're also trying to bring in some traditional methods for exploring liquid crystallinity in material systems to look at the polymer in very concentrated solution as well. And the results are very preliminary at this point. They look, I would say, interesting, but there's nothing definitive at this point, so we need a little bit more time to investigate. But yeah, deconvoluting the current measurement versus isn't that easy.
Last questions? Let's thank Elsa again.